So now we start with the presentation. So this presentation will show you some of the basic features of FENX, then a basic intro of what we are planning to do today in this session. Okay, so I'll be your host. My name is Chinmoy and I work as a senior geotechnical engineer in Midas IT, India. So as you can see from the diagram here, our main goal is to demonstrate the applicability of soil structure interaction related studies and the integration between Midas Civil and FENX. So that leads us to the agenda that we have planned, on a phase by phase manner. So with the introduction, I'll talk a brief about FENX, some background about solid structure interaction and its fundamentals, and we'll have a brief intro of civil and FENX model. Second, in the numerical model description, I'll show you the model from civil, then the meshing technique in FEA, the loading scenarios that have been imported from Midas Civil, and then the boundary conditions that have been incorporated in FENX. Finally, in the analysis and output, I'll show you the construction stages planning, then the interpretation of FEM results or the graphical output plots, then some basic forces envelopes on the piles, the pile cap and the piers. Okay. Finally, the charts. So now it's time to start with the introduction to FENX. So what is FENX? FENX is a powerful software or a tool that has all the elements or aspects needed for successfully conducting a finite element model, be it a structural one, be it a geotechnical one. So to conduct any finite element analysis, you need to have first a geometric modeler. As you can see from the images depicted in here, the FENX has a powerful CAD input platform that can let you generate very complex images or geometries. From there, we go to meshing. FENX supports auto meshing or map meshing and also the manual meshing mode. Then the preprocessor for FEM, it develops the boundary conditions, the loading conditions, and then the analysis cases definition. So pre-processing is anything that comes before the actual solving of the equations start. So for the equation solvers, we have the two meshes which convert the geometry into the FEM model. For post processing, as you can see, we have the graphical output plot. So that will show you, what kind of results are happening in which part of the model. Finally, in the report generator, you can see the displacement results, the vector graphic plots, the result tables or charts or things like that. So FENX to successfully deliver these results has to support a multitude of analysis types. In terms of analysis, you can go for a static or a nonlinear static analysis, construction stage analysis, then reinforcement and buckling analysis. Then we have the dynamic analysis part where we have the eigenvalue and the response spectrum analysis, the time history analysis, which contains ground acceleration data from previously happened earthquakes. Then you can have contact analysis. Then you have concrete crack analysis, the heat of hydration analysis, and heat transfer analysis. So these all cater to mostly structural engineers. Now coming to the geotechnical part, you can do the slope stability analysis or seepage or consolidation or coupled analysis. Right now you can see on the right there are three images. One is for the bridge deck, second is for the gates of a dam, and third is for construction joints. So all of them can be easily accomplished using the FENX software. Starting with the advanced geometry modeling features. So you can develop lines, arcs, ellipse, or tunnel profile sections from the inbuilt tools that have been provided in FENX, or the B-spline or polylines, rectangles, or profiles. Similarly, to create from 2D to 3D, we have a lot of options like loft or sweep along a guided line. Okay, like you can see, you can easily create a section of a bridge or the tunnel section, also incorporating the things like the cross passage. Okay, then for modification we have the fillet and chamfer option, the merge and break option, the intersect and the make wire options. After geometry, we'll proceed to the meshing features. On the left side that you can see, like the these ones, these are the tetrahedral meshing parts. So the tetrahedral mesh means we have six noded elements for each section of the mesh, and they are successfully used in other softwares too. So apart from this, GTS NX also has a complicated meshing scenario, that is the hybrid mesh. The hybrid mesh has eight noded elements. That means you have more nodes for lesser number of elements. That is why the computation time is a bit lesser for the hybrid elements, and also the results are a bit more clearer. Again, the results between the hybrid mesh and the tetra mesh would not make much of a difference for the exact same type of mesh size and analysis. What will differ is the total number of nodes in each of the element choice type you have. So any complicated geometry can also be meshed, like the one you see in the shaft sections or the construction joints, or for this case like a tunnel and its cross passage intersection. Similarly, things like this erosion protection system for our coastlines or a very complicated slope. So after the meshing part, we'll go to the material library. The material library of FENX consists of both geotechnical and structural modeling elements. So for elastic, we have linear elastic, transversely isotropic, or Jardine or hyperbolic functions. For plastic materials, we have wall matches and Tresca for the structural elements or the structural engineers work. For pure soil modeling, we have more column. Then we have CAM clay for clay type soils. We have soft soils. Then we have modified more column and hardening soil for the hardening soil material types. You can also incorporate undrained materials in the model for if you want to accurately represent the undrained shear strength of soil. For functions, we have non-spatial functions. We have functions for pile and pile tip bearing functions. Then you can also incorporate elastic functions for truss, point spring, or elastic links. Also, for people who are working with dams or seepage methodologies, you can use the Gardner coefficients or the frontal functions or the Van Genneken functions to define your soil water characteristic curves or SWCC curves. We also have strain compatibility functions for 2D equivalent linear modeling. Next, we'll come to the sections database. So any section, or I would say most of the sections are directly covered under the database. We also have a big database of the various codes like the ASTM code or the BS code or the Indian code or the Canadian code. And apart from that, a T section or a I section or a pipe or a H section can directly be incorporated into FENX. So here all you need to do is just enter your data for the section, and the stiffness constants will be calculated directly by FENX. Okay. Finally, after this, one of the main tools that we need to refer to is the product integration. That is why we are doing this webinar today. So product integration means if you have done something in Midas Civil or Midas Gen, you need to be able to bring that to FENX. So this is aptly demonstrated by the two models in here. On the left, you have the Gen model on top, and on the right, you have the complete GTS model. On the left bottom, you have the cable straight bridge design from Midas Civil. On the right, you have the ground incorporated to check for the various deformations caused by your presence of the bridge along with the load applied to it. So you can see the ground here is quite complicated. It is not exactly something that you can enter or in data and then get the result. For this, we have certain tools in GTS NX or also in FENX, which I'll show you later on while I demonstrate the model to you. So this was all I had to show about the FENX introduction. Next, we will come to the main topic of today, that is the SSI. So what is SSI or solid structure interaction? We will like to start with the background. So what is SSI? SSI is nothing but the interaction of stiffness and deformation between structure and soil. It is necessary to adequately assess the stresses and forces in the supporting structure. So why do you need SSI? Because we also need to check for the supporting soil that generates loading and provides a resistance to loading, because any structural element is only going to transfer the load to the soil. That is why it is very important to check for the soil structure interaction. Next we'll come to the methods of SSI. So there are basically two methods, that is the substructure method and then the direct method. Substructure method has a classic example of something called as p-wide nonlinear analysis. That is nothing but based on your Rees et al. Theory or Rees and Matlock theory. So in that, what you can do is you can just model the soil as spring dampener system with response, and the detailed structure is designed with the idealization of the soil as independent damper springs. So based on that, you will get your uh, py curve for every node you have created along the length of the pile. Now we come to the direct method. So in today's session, we will cover the direct method. That means the continuum method, or in other words, we will introduce the soil profile along the structure to check for the accurate deformations or plasticity along the soil due to the presence of the big structures. Numerical methods like FEM are and FDM, or the FEM for finite element and FDM for finite difference method, they are very strong and astutely connected in a fact that you will get very accurate results based on your immediate requirements. And the entire soil structure system is modeled and will be analyzed in directly one step. So whatever loads are happening on top of the bridge will be transferred to the soil via the foundation elements, and we will check for the ground deformations using the vectors, also using the graphical contour results of the software. So the direct model of the soil structure interaction will look something like this. Let's say it's an example of a bridge. We just along the bridge we transfer the reactions to, or the loading scenarios to the FEA model. Then from the FEA model, after you have successfully run the analysis, you then send the force displacement curves to civil, and there you can check the graph for the nonlinear p delta curves. Okay. Otherwise, the same thing is also applicable for Midas gen. Let's say if you have a gen structural model for a building along with piles like this, you can import that into GTS NX along with all the forces or reactions like this, and then you can export the force displacement curves back to gen and then look for the actual graphical output in there. So it is quite simple, and the methodology is also very simple. As long as you have your civil and gen model defined, you can directly send it to GTS NX or FENX and then directly export the results back to to civil or gen. Finally, the advantages of direct method. There will be some pros and some cons, just like every other methodology used. So the pros are, for a fully coupled analysis, you will get a direct result. You can also incorporate things like groundwater into account. It reduces the overall simplifications or assumptions done to the model. The more you simplify or assume a field behavior, the chances are the more negative results you might get. So redundancy is avoided in here. And plus it takes into account the nonlinear behavior of the structures and as well as the soil. The cons are it requires a very good solver. Otherwise, chances are you might crash the computer. Otherwise, also one of the cons is that it is a very complex and time consuming process. Depending on the type of structure you have or depending on the ground data you have. It can be simplified, it can be complicated, just like any other finite element model. So before we jump into the numerical model, I'll just show you the workflow process. So we start with the geometry. Either you can import or create a geometry in FENX. Then you create the material properties attributes for the ground elements or the structural elements. Okay. Both part 2 and part 3 are interconnected. So they can be, done at the same time. Then the fourth will be the meshing part. In the meshing, you use the mesh control or you just mesh the geometry using auto mesh option based on how you feel necessary. Then you go for the loading and boundary conditions. So in the geotechnical modeling, we normally go for roller supports on sides and fixed supports on bottom, but obviously that is not exactly valid for structural elements. So it depends on what kind of ground boundary conditions you want to provide to your model. Finally, after that, you come to the analysis creation part, and then the software or the solver solves the analysis for you. Then the results, where you get the contour maps, the probes, and the reports. So the first part of the PPT is over. Now we'll go to the numerical model description. So let's say this is an example of a civil model for a bridge. The main span and the deck are shown on the top. Then this is the pier cap. Okay, these are the piers. Sorry, these are the piers. Then the pile cap. Then the piles. So in short, the bridge is supported by piles and abutments on each side. And please do remember all the loadings will also be imported along with this model to FENX. Now coming to the meshing part. So I mentioned something about the hybrid mesh from the very first. So this is how the hybrid mesh looks like. So in the hybrid mesh, you have both the tetrahedral element and the hexahedral element joined by a common base, as you can see in this part. So here what it gives you is that you have less number of element but exactly same number of nodes or higher number of nodes. That is why you have a faster computation time. Secondly, after meshing, we go to the loading conditions. The loads have been imported from Midas Civil as shown in here, and the GTS model with the ground element intact looks like this. Then in the boundary condition, it is very simple. In FENX, we just go to constraint, we click on auto constraint, and the software will automatically generate roller supports for the sides and the fixed support for the bottom. That's it for the inputs. Because most of the inputs are already there from the civil model, so all you need to do is just create the soil around it, mesh it, give it the boundary condition, and also give the groundwater condition if applicable. Here the groundwater is around 1.5 to 2 meter below the actual ground level or the outcrop level. So after the boundary conditions have been defined, we'll go to the analysis and output option where we will start with the definition of construction stages. For the construction stages, we have used the non-linear static type analysis for four conditions. First is the in situ ground condition. That means the virgin ground condition. There is nothing present in the ground and the ground will look like this. Okay. So after that, the ground will have the foundation elements incorporated into it. That means the piles and the piers and the pier cap. Then the bridge is laid upon, and in the final stage, we activate all the loads on top of the bridge or on the span. Okay, so these four will be your construction stages for which we'll try to check the deformation of the ground. So the deformation can be shown as an animation as shown in the next slide, like this. So these animations can be downloaded into a video format or a GIF format based on how you feel necessary. So it will show you the genesis of deformations from start till the loading phase of the building, or sorry, the bridge. In terms of results, you will have the results for the pile, you will have the axial loads and the bending moments. Then for the pier and the pier cap, you will also have the axial loads and the bending moments. So this is your pier cap and these two are your piers. Okay, after all this is done, what you do is just export your force displacement curve data to civil and you can get a graph like this. Again, this is not exactly too non-linear, but it also depends on the loading applied. In this particular model, the for demonstration purposes we didn't apply a very high loading to the bridge, so yes, it is kind of like this. It's mostly, one can say it's linear, but yeah, based on your loads it can also go on something like this. Okay, so these output graphs, they mostly depend upon your input data. So I hope everyone enjoyed the presentation. Now we will start with the numerical model.
The broadcast is now starting. All attendees are in listen-only mode.
So now the presentation is complete and we go to the numerical modeling part. So we have to develop something like this. So your results might change based on what inputs you want to provide. And again, FEM is a very subjective solution. So results always change a bit when the hands change. So we have to accept a 5 to 10% deviation in the acceptable results limitations. Now, to reach here, as we have mentioned, we are doing SSI, so we have to start with the civil model, and we'll plan to do something like this. Okay. So what I'm going to do now is I'll just open up Midas Civil. So the bridge along with the foundation elements are seen here. The piles, diaphragms, the abutments, and then the span girders and the cross beams, the piers, pile cap, pier cap. Okay, and all the loadings have been applied in here as the static load cases. So what we're gonna do is we'll just go to the civil icon, we'll click here, we'll export this as MXT file for FEA or GTSMX. I'll name it as, let's say, ABCD. Save. It takes a couple of seconds for Civil to convert that. You'll also get a generated text file like this, with the nodal locations and all the beam element forces like this, along with the locations or the nodal locations for each of the applicable elements on the, sorry, applicable nodes where the force is being applied. So that's all for the civil part. We'll conduct everything else in FENX right now. So I'll just go to FENX, and FENX is a multi-tabbed window option. Okay, so what I'm going to do is just click here. I'll go to new and I'll select 3D. For the unit system, you can also have imperial units if you want, but I prefer working with the SI units as I find it more comfortable. So I'll just press OK in here, and our GUI, it looks like this. Left is the workplace, okay, the properties pane, or this is the output pane, and top is the ribbon menu pane. So I'll click on FENX. I'll click on import. In the import option, you can see we have options for everything: CAD file, a 2D or 3D DXF or a DWG. So here what we're gonna do is we'll click on Midas MXT file. Okay, I'll go to here. We'll wait for a couple of seconds. So this is it. Okay. So in the default mesh, you can see the cross beams, span 1 girders, span 1, point springs, elastic link, rigid link. I'll hide the elastic and the rigid link. In the analysis, as I defined before, the loads, the loads have been imported too. Okay. Now, before going for this soil modeling, I like to, distribute this part, the entire default mesh into a few more sub meshes. So GTS and FENX both allow you to do that. I'll go to mesh, create, right click, create a new mesh set. I name it as piles. Okay. Then a new mesh set. I name it as F2 pile cap. Then a new mesh set and one more. I'll name this as piers F2 pier cap. If you also want to separate everything for a conventional construction stage method like the one I showed you, you also need to separate the abutment. So I'll create a new mesh set for the abutments. Abutment. Okay. So now it's time to add elements to the mesh sets that we created. In other words, the elements are already there. We just need to separate them. So I'll click on right click on piles, click on include extrude element nodes. Okay, like this. Press OK. If I select on piles, you can see the elements are added to the pile now. Now time to select the pile cap element. Same drill will be applied in here. Okay, we have selected the pile cap. Now the pier cap. Again, it is mostly for a convenience of modeling. Otherwise, if you don't want to separate them, it is still fine. Now the piers. Okay. Then finally the abutments. Okay. So if I go to property and I click on piles, pier cap, abutments, okay, pier, pile cap, and I activate them. Piles, pile cap, pier, pier cap. You can see they look like this. And they are connected to the main bridge by the rigid links. Again, we have done nothing in here, but just separated everything. So next what we do is we create the ground profile. So I'll just hide these for now. Okay. I'll also hide the loading conditions. I'll also deactivate the rigid links. So I activate the grid and the coordinate global axis. I'll go to top view. So what we do now is we just increase the size of the grid. I'll click on define grid, choose the grid size as 10 meters, user defined, let's say it is 50. So 10-meter grid size and 50 units. So what I do now is I'll just create a rectangle to simulate the ground profile like this. Okay, so what we do now is they need to share the nodal connection with the foundation element, that means the abutment. So our goal is to ensure that the node sharing from the abutment from this part and the pile is present with the ground. So for that I just need to know the location of the abutment. For that I just go to create a point and check for the z-axis coordinate on the bottom, that is minus 6.8. So what I do is I'll go to translate, select this direction z, distance minus 6.8, press OK. Okay, so that means the ground and the foundation elements are at the same level right now. If you want to verify that, you can also do it like this, pile cap, okay, the abutment like this. So next what we do is just create a solid out of it. I'll go to extrude, select the face, direction being minus z, and length let's say is minus 40 meters. Okay, so now you can see my solid is complete. So in terms of geometric part, that is all it is needed. So next what we do is, if you have a uniform ground profile you can do that, or otherwise if you have multiple soil layers you can also incorporate that, or if you have your borehole data then you can also develop your own soil model. I'll just show you an example of incorporating borehole data. So let's say I hide my geometry. Okay, activate the grid and this. So let's say I have borehole locations at 4 random points, one being at minus 10 0 0, okay, and minus 20 0 0, and the third being 60 0 0. We know that our ground starts at minus 6.8. So what we're going to do is we'll just transport these three into the same level as the ground level. So what we're going to do is we'll click on translate, click on these three, direction again the z-axis minus 6.8. Okay, so we'll hide the mesh and the grid. Now we want to create our ground profile. So we'll go to bedding plane wizard. So in the bedding plane wizard, all you need to do is just define your bedding planes, and the software will extrapolate your planes for you. All you need to do is just enter your borehole log data in here. So let's say I name the first as 11, name of the first borehole is 1, location is this particular borehole. Okay, so let's say the depth of my first layer is 3 meters, second is 6 meters, third is 19 meters, okay, and fourth is let's say 50 meters. Now we'll create our second borehole, that is in here. So location being 20 0 minus 6.8. The first layer let's say is 5 meters deep, second layer 12, third layer is 16, sorry, third is let's say 24, fourth is let's say 60. Okay, and our final borehole name is number is 3. Double click here, same thing, just need to enter the depth in here. Let's say the first is now 7 meters, second layer is 14 meters, third layer is 27 meters, fourth layer is 65 meters. Okay, you press on modify, and here in the axis notation we need to define how long will be the stretch of the borehole data. So let's say it ranges for 70 units. So I'll do a preview of that first. If you go to side view, these are your borehole data. Okay, like this. So you can use that too to create your solids. Okay, I'll just press, let's say I create a new geometry for this, and if you want to define your solid based on this, just click on the solid. Okay, let's say I use these two boreholes for my data analysis or the soil stratigraphy definition, because this one is clearly outside, so we don't need this particular. So what I do is, again the first one that I had hidden, it was quite random. So if you have your borehole data, you can directly create something like this, shouldn't be a problem. So to create the accurate ground representation, I just need to go divide solid, click on the solid, select the tool surfaces. Okay, I'll press okay. You can see my solid is now 3 layers. That means I have the soil stratigraphy embedded into it. Okay, so that's how you can easily replicate your soil stratigraphy based on your borehole data locations. Again, for your bridge analysis, your borehole data locations might differ. So as long as you have the coordinates, you can easily create your borehole logging into here. Now I'll just switch uh, the borehole data from here. Okay, so I'll just delete what I don't need. That means the borehole logging data. I'll only have one ground layer, for simplicity of the modeling. So let's say you have divided the solid. Now you want to patch them up again. What you can do is go to Boolean, select the 3 solids. Okay, click on merge faces, press OK. It will become a single unified solid again. Now I'll go to the meshing part. So I'll hide the default mesh and the mesh that we don't need for now. We only need the mesh around the pile cap, the abutments, and the piles. So I'll hide everything else. So what I'm going to do now is I'll go to geometry, point, convert node, select, my bad. So what I'll do is I'll select all the points that fall on the vicinity of the piles and just on the link between the ground and the abutment, like this. Okay, I'll press OK. Like this. So after this, what we do is we'll directly go to meshing. Nothing else is required. So we'll go to mesh, material properties. We have the properties for the that were imported from civil. So we just need to create a ground property. I go to isotropic. As I mentioned, you can have any property you want in here for soil and rocks. For rocks, we have the Hoeken-Brown, generalized Hoeken-Brown, and also the CWFS. If you want to check for liquefaction, we have NORSAND, PM for sand, and the modified UBC sand model. But here I'll just use a simple Moore-Coulomb model. Okay. and name it as soft rock. So I give the elastic models as, let's say for soft rock it should be around 0.5 GPa should be a good one. Name it as 500,000 unit weight. Let's say 23.5 non-linear. Let's say the cohesion for soft rock still will be around 40-50 kPa. So I use 45 kPa. Frictional angle 39 degrees. Okay. Saturated unit weight, let's say is 24.5. And the permeability, I just leave it as default. You can always change it based on your requirement. But 1e minus 5 meter per second is a good enough of, approximation for soft rock permeability. That will be on a, or cracked rock or fractured rock permeability. That will be very close to something like that of sand. So I press OK and I close it. Go to property. I'll just create a 3D property naming soft rock. Press OK. You can see it is created now. Now it's time to mesh. I'll activate the solid. Okay. Go for 3D mesh. Select this. So I give a mesh size of 2 meters. I'll choose the hybrid mesher and name it as ground. And I click this one because we need to incorporate the pre-existing mesh with the new mesh. For that, the nodal connection will be formed along the points that we had created using the convert node option. So we'll click on interior edge, select all the points. Okay, and I click on consider imprinting shape on face. Press OK. Press OK. It will take a few seconds to mesh that because there are large number of points at where nodes will be created. So there we have it. Since this is a finite element modeling, you have to ensure that the ground mesh also shares the nodal connection with the meshes of the structure element or the civil elements that we imported, like this. Okay. Now our meshing part is complete. So what we'll do next is go to analysis. In the static analysis part, we click on constraint, go to auto constraint, name it as BC, press OK. Or the boundary condition. Roller supports on sides, fixed on the bottom. So the static loading condition that we had imported will look like this. So after this, we'll define our construction stages. I'll go to stage set and name it as SSI. I'll press add, the type will be stress. I'll go to define CS or construction stages. Before that, I'll just pan the model to the right. I'll click on define CS. In the first, we will have the in situ condition. So we'll only activate the ground and the boundary condition and the self-weight loading. In the show data option, if you click on activate, you'll only see the activated parts. Click on clear displacement. If you want to define a water level, let's say the water level is 2 meters below. I press it as -9 meter. That is still fine. Press save. We name it as in situ. Second will be our foundation. So here we activate all the foundation elements. So I activate the pier cap, the pier, the pile cap, and the piles, and the abutments. It is completely subjective. If you want, you can also add one more stage and then activate the piers and the pier cap. But I just did that all the substructure completely together with it. So I hope it is fine by all of you. Again, press save. Then new the deck. Activate the girders, the cross beams, all the and the girders. Okay, and the span one. And the default mesh set. So before this, I actually forgot to activate the elastic links and the rigid links. We'll activate that here only. So now the bridge is activated. Finally, the loads. We'll activate all the loads here. Okay. I'll apply the load in increments because soil doesn't have very high stiffness. So there's a chance that you might get, divergence. For that, always apply the load in 10 to 20 increments. So apply the load in 10 increments, press OK, press save, then I close it down. I close it down. Okay, all we need to do is now just run the analysis. We go to analysis case, press add, construction stage. I name it as SSI. In the output control, we activate the soil strains. And that is all. Press OK. Then you can just run the analysis case. But we have already run that, so just look at the results now. So in the first stage, as we mentioned, it was for in situ ground conditions. The displacements will be 0. All we need to do is just check for the prevalent ground stresses. So the horizontal stress, vertical, again the transverse horizontal stress, the vertical stress, and then the pore pressure. Since there is no there is no clay type soil in here, the pore pressure will be uniform, and there will be no excess pore pressure developed in here, but there will be development of negative pore pressures on the top of for due to capillarity. And please note that in GTS the pore pressure on towards the down is negative, towards up is positive. So with the foundation activated, the ground displacements look like this. Okay, the total translation, the settlements. Okay, then if you want to check for the forces, you can also do that. Let's say if I just deactivate everything, check on the piles. These are the axial loads on the piles. Then the bending moments. Okay, then the shear force. You can check them like that. Now when the spans are activated or the deck is activated without the loading, obviously, the ground deformation is in the tune of 11 or 12 mm. Okay, same thing, you can also look for the axial loads on the piles and also on the pier. Now you have to check for the pier, the axial force on the pier, on the pier cap, on the piles. Okay, same thing, bending moment, shear force can also be seen. Finally, the loading stages, we'll just focus on the last stage, total deformations. Okay, look like this. Ground settlements. If I just switch off the and only focus on the ground, they look like this. Here we also need to check for plasticity points. The higher concentration of plasticity points means the ground is in the unstable zone. If I go to plastic status, you can see there are very few plastic points, so which is a good sign. Now, after this, what we need to do is to successfully conduct our SSI, we need to export the results. So for that, what we will do is we'll just click on File, Export. We'll export the nodal results. Okay, you can either export the reactions, but I'll recommend. But for PY curves, you need to export the force displacements and whatever components. You can also export all the components. Press OK. So after that, you have exported. What we need to do is they will be saved as a dot as a text file. So I'll just show you how the text file will look like. So this is it, the text file. Okay, the nodal locations and the force displacements per to each node will be exported. So after that is done, all you need to do is just go to civil, press on the civil icon, import nodal results either for GTS or FENX. So I'll just click on for civil, press open. It'll take a couple of seconds to open up. It's done now. So what I'll do is I'll look for the force displacement curve. Okay, click on boundaries. Okay, all the springs are present here, all the rigid links. Then the force deformation functions. Okay, you can just click on any random node in here and you'll get your force deformation functions. So this is how you can conduct your SSI. Apart from that, if you want, I'll just show you an example. You can also do seismic analysis, for time linear or non-linear time history analysis. So here, this is a model from Midas Gen that we had imported. So we had done both, the eigenvalue and response spectrum analysis. So if I just vary this one, you can see the changes in deformations due to the earthquake. So, all this kind of analysis can be done in FENX, and you can always export your data results to GTS from FENX or GTNX to Civil or Gen.